Okay, so not sure if this is going to be a quick video. Feel free to fast forward to whatever parts you need on this one. So we did all of B4, numbers 1 through 14. So number one, the work done to compress a sample of a gas is 50 joules. So when they say compress, that means work is being done on the gas. So remember, our standard first law of thermodynamics equation is the change in internal energy is equal to the heat added to the gas minus the work done by the gas, so expansion. So in this case, we are compressing, so I'm going to assign a negative value to what they said, the number they gave me of 50 joules. So during the compression, an energy of 30 joules is transferred to the gas from the surroundings. So we dumped heat into the gas, so that's going to be a positive sign, minus a negative 50, so that gives us plus 80 joules is our change in internal energy. So not only did we heat up the gas, but the gas was compressed. And compressing the gas, we would expect it to heat up. So we got the double whammy there, and 80 joules of energy, which was answer D. For number two, a quantity of 0.06 moles of monatomic ideal gas has a fixed volume. 40 joules of energy is supplied to the gas. State the work done on the gas. So they said fixed volume, so no work is going to be done there. So that's A. A is just 0 joules of work. For B, calculate the change in temperature of the gas. So the change in internal energy is equal to Q minus W. So the change in internal energy has got to equal Q, since there's no work done. And did I actually need that? Yes. And then the change in internal energy is just going to be U final minus U initial. So remember that the internal energy of a gas is 3/2 nRT. So that could be 3/2 nRT final minus 3/2 nRT initial, which is just 3/2 nR change in temperature. And we don't know the change in temperature, but we know that we know N and R, and we know that the change in internal energy is equal to the heat. And since we have 40 joules of heat are added, supplied to the gas, we can just set that equal to each other. And when we solve that out, we get a change in temperature of 53.5 degrees Celsius. For number three, we have 0.03 moles of monatomic ideal gas is compressed. The temperature of the gas increases from 20 to 90 degrees Celsius. The gas does not exchange thermal energy with the surroundings. So Q's got to equal 0. So that's what I did right here. So that means our change in internal energy is negative W. Since we're compressing, the work is going to be negative, which makes this positive here because negative of negative W. And we know the gas does not calculate the work done in compressing the gas. Well, the work has got to be the change in internal energy. And from up here, we know that our change in internal energy is just 3/2 nR times our change in temperature. We know our change in temperature is 70, and we know the number of moles. So when you work that out, you get 26.2 joules. Number four, quantity 8 times 10 to the negative third moles of monatomic ideal gas in a cylinder compressed by a piston. The work done on the gas is 7 joules, and the temperature of the gas increases by 50 Kelvin. So calculate change in internal energy of the gas using the same equation we just used previously twice. So then change in internal energy would be 3/2 nR. Sorry, that should be a change in T right there. So we work that out, and that's about 5, so 4.986. And then we can do the energy transferred between the gas and the surroundings during the compression. So they are asking for how much heat got transferred out of the gas. So we know our change in internal energy is 5. The work done on the gas, so because the gas is going to be compressed here, we're going to put a negative sign for that work. So that ends up being positive. And in this case, the change in internal energy of the gas, so it looks like we removed, so when you work this out, we removed 2 joules of energy from the gas. Does that make sense? Monatomic ideal gas compressed by a piston, so it should heat up. And, oh, I see. So that does make sense. So it is going to heat up, but it didn't heat up as much as it would have if we hadn't taken some energy out of the gas. And then for B, the gas remains compressed at a constant volume. Its temperature increases by another 50 K. State the energy transferred to the gas. So when they say compressed at a constant volume, that means that no work is being done. So any energy that's transferred out must be the same as what we calculated earlier, because we have that same change in temperature value. So we just got 5 joules there, because we're staying, no more work is being done. So the change in internal energy will just equal Q. All right, number 5. Monatomic ideal gas expands at a constant pressure of 1.2 times 10 to the 5th pascals. The initial temperature of the gas is 300 Kelvin. And the initial volume is 1.5 times 10 to the negative 4. So I try to draw a little diagram for these. I got my axes labeled. That's 10 to the 5th pascals, 10 to the negative 4th meters cubed. And they told me the area was 6. We actually solved this one, or students solved this one in class, I forget who. But calculate the number of moles of the gas. So we just do PV equals nRT. We know PV, R, and T for this initial point here. 1.5, 1.2. Work all that out, and you get 7.2 times 10 to the negative 3 moles. So that was A. And then it says the work done by the gas during the expansion is 6 joules. So this is an isobaric expansion. So we can just find that area underneath. That area is equal to 6. And so area is base times height. In this case, our isobaric, or our pressure is 1.2. So that's going to be our height. And then our base is 1.5 times, or sorry, the high value minus that. So essentially our change in volume. And so our change in volume is 5 times 10 to the negative 5th. Change in volume is V final minus V initial. We know our initial volume and we know our change in volume. So we can find our V final is 2 times 10 to the negative 4th meters cubed. So that's the final volume of the gas. The final temperature we can do with just PV over T is equal to PV over T during this state, this change here. So we know our initial pressure is the same as our final pressure. Those cancel out. We know V initial, we know V final, and we know temperature initial is 300 Kelvin. So looking at that isotherm right there. And when you work that out, you find that temperature final is 400 Kelvin. And the energy transferred to the gas during the expansion, now we're going to use our first law of thermodynamics. So change in internal energy is equal to Q minus W. We know 3/2 nR times the change in temperature. We know our change in temperature goes from 300 to 400, so that's 100. And we know our number of moles, and that's going to equal Q minus 6 because the gas is definitely doing work on its surrounding. So the work done is positive, so it'll be minus 6 there. And that means we had to dump about 15 joules of energy into this thing to get it to do that work and raise its internal energy. Number 6, cylinder with a movable piston contains an ideal gas. And the cylinder is placed in a cold environment. Thermal energy is removed from the gas. The volume of the gas decreases from 1.8 to 1.4. So again, I did my little diagram here. Constant atmospheric pressure of 1 times 10 to the 5th. So again, we have an isobaric process. Calculate the work done. Well, you know the base and the height of this. So that area is going to be 40 joules. The final temperature of the gas is 260. So what I did was I drew a little isotherm right here for my final point is 260 joules. Calculate the initial temperature. So in this case, you know, I went on the wrong track here. I actually calculated the number of moles, but I didn't actually need it because I can just do PV over T again because it's the same thing. My pressures are the same. I know my volumes, and I can find my temperatures. Did I have to do that? It says the final volume of the gas. Oh. Yeah, I didn't need the number of moles. So I could just do PV over T is equal to PV over T like I did before. And then the energy removed from the gas is 100 joules. So they took out, so Q is negative 100. And calculate the change in internal energy of the gas. So negative 100. And the gas has work done on it because it's being compressed. So that W has to get a negative value because it's being compressed. So that ends up being negative 100 minus negative 40. It's going to be negative 60 joules. All right, these charts right here for number 7 are really, really good for cycles. So hopefully I'm going to use them a lot over the next few problems, and hopefully you will start to use them as well. So for number 7, ideal gas undergoes a cyclic process, consists of adiabatic compression from A to B, an isovolumetric process from B to C, and an isobaric expansion from C to A. So it says the table contains some of the data about the process. Q is the energy transferred to the gas, delta U is the change in internal energy, and work is work done by the gas. So they gave us 970, negative 1570, and 1000. So what I did was I just labeled the boxes 1, 2, 3, 4, 5, and 6. So for 1 and 2, we have an adiabatic process because AB, they said, is adiabatic. So if it's adiabatic, Q's got to be 0. So there's got to be a 0 in that spot right there. And then you can just plug in. You know that delta U, change in internal energy, is equal to Q minus W. Well, change in internal energy would be equal to 0. That's how much heat you're adding, minus negative 970 because the gas is being compressed. So you're going to have 970 joules. You should expect that gas to heat up. And as you see on here, it is. It's going from a lower isotherm to a higher isotherm. So it's heating up. So we dumped in 970 joules of energy, or essentially the internal energy increased by 970 joules. For 3 and 4, this is BC, so this is isovolumetric, or isochoric also. So if it's isochoric, then there's no work. So that's got to be 0 right there. So we look at our first law of thermo. Change in internal energy is Q minus 0. Well, if you know your change in internal energy is negative 1570, then your Q's got to be negative 1570. And this makes sense because this gas is being cooled down. It's going from a high isotherm to a low isotherm without doing any work. So heat must be pulled out of it. So negative 1570 joules. Now, here's the key. For 5 and 6, what you got to remember is that if you start at A and you go A to B, B to C, and then you go back to A, then the overall change in internal energy for the cycle has got to be 0. So we have for up here, it's 970. Here it's negative 1570. So that must mean that these all have to add up to 0. So 5 has got to be 600 because, again, they've got to add up. So 970 minus 1570 plus what is going to equal 0? That's got to be 600 joules. And then once you have that, you can figure out how much work was done, because you know your 600 joules is equal to 1,000, because that's how much heat was dumped in on C to A, minus the work done. So the work in this case, it is expanding. It's doing work on the surroundings. So the work done there had to be 400. Again, these are super powerful for cycles, mainly because that middle column there, or wherever you decide to put it, it's got to end up at 0 when you add them all up. Finally, for the second part, what was this, part B? Determine the net energy that leaves the gas during one cycle. So you have negative 570. Wait, where's our chart? So what was 1? 1 is 97. Oh, no. 1 is 0. 3 is negative 1570. So, and you got 1,000 there. So 570 joules is leaving. Because your net Q is negative 570, so your net is cooling here. And if you look at that, the pathway here, this is a refrigeration process, right? If you're going counterclockwise through your cycle, you're refrigerating. If you're going clockwise through your cycle, you would be a heat engine. All right, 8, monatomic ideal gas compressed at a constant temperature. 346. So I drew this isotherm here. That's my 346 isotherm from A to B. We know the pressure and we know the volume and the final pressure. The isothermal compression is followed by an adiabatic expansion to a final state of C of volume 5 times 10 to the third. So it comes back to its original volume here. And calculate the pressure at B. So just use PV over T. And when you do that, you have the pressure, you got the volume. The temperature is the same because it's isothermal, so the T's cancel out there. For part B, the temperature at C, in this case, I actually read the graph. If there's another way to do this, please let me know. I just looked at the graph because at point C, it was clearly, it's at the same volume, and it looked like about 1.2. So my answer is a little bit off in the book, and sorry I got a little lazy on this one. There might be a better way to figure this out a little more precisely other than reading the graph. For number 9, ideal gas undergoes adiabatic compression from A to B, isobaric expansion B to C, and isovolumetric process from C to A. So that would be, I call it an isovolumetric cooling, but they call it a process. The volume at A is 6 times 10 to the negative fourth, so I put that on here. Here's my axes. Pressure at A is 2, so I got that over there, and the pressure at B is 6. All right, so calculate the volume at B. Now, make sure that you read this part. For adiabatic, they talk about this relationship here, PV to the 5/3 is equal to a constant. So you could say what the process is, adiabatic compression. So from A to B, you could say PA VA to the 5/3 is equal to PB VB to the 5/3. And make sure you're good with these, the way to put these into your calculator. So when I solved this out, I got 3.1 times 10 to the negative fourth meters cubed was my volume. This 5/3 refers to monatomic gases. If you do a diatomic gas, I believe it goes to 7/3. Explain why the temperature at B is greater than A. So you've got work being done on the gas, so it's compressing, molecular collisions are increasing, the speed of molecules got to be increasing, so kinetic energy, internal energy has got to be increasing. So that's why it's heating up, or the temperature is going up. For C, calculate the work done during the process BC. Well, that's the area underneath there. And since we now know our volume at B, we know our base and we know our height. And so just multiply that out. And I got 174 joules. Since it's expanding, the gas is doing work on its surroundings. So that's going to be positive 174. For D, the work done on the gas during the process AB is 99 joules. Calculate the net work done on the cycle. So net work is going to be 174 minus 99. Essentially what's happening is you got to take this area and subtract off the area underneath this curve, which they told you was 99. And finally, I filled out this chart because they said the energy that leaves the gas during the process, CA, is 360 joules. Calculate the energy transfer of the gas during the process, BC. So I just set up the chart again like I did last time. We know that these all have to add up to 0, and that gives me some vital information in filling this out. AB was adiabatic, so that was 0 there. So that means if this is 99, then that's got to be negative 99 because work is being done on the gas to compress it. The last one was energy that leaves the gas during the process is 360 for C to A, so that's negative 360. And since it is an isovolumetric process, work has got to equal 0. So that means that that's got to be negative 360, or change in internal energy, because we pulled that Q out, so it must have cooled the gas down, so the internal energy went down. And then because I know those, the 99 and the 360, I can figure out the 261, okay? So the change in internal energy from B to C has got to be 261. That allowed me to fill that in right there. And what were they asking again? Oh, yes. And we know how much work is done during B to C. So we know the work and we know the change in internal energy. We can just go back to first law of thermo. 261 is Q minus 174. So the amount of heat that we put in must be 435 on B to C. For number 10, work done per cycle of a reversible heat engine is 5,800 joules or 5.8 kilojoules. Engine rejects energy at a rate of 2,400 kilojoules per cycle into a cold reservoir to keep it at a constant temperature of 100 degrees Celsius. So here's our heat engine. We go from a hot reservoir to a cold reservoir. So QH comes out of the hot reservoir, goes into our engine. The engine does work for us and expels amount of heat at lower energy, 2.4 kilojoules. Calculate the energy transferred to the engine from the hot reservoir during one cycle. So this is just conservation of energy written a different way. Like if you look at this, you know that this energy right here, I didn't do a good job of the arrow widths on this Sankey diagram, but QH equals QL plus work. And we know how much those two are. So QH must be 8.2 kilojoules. Calculate the efficiency of an engine. The efficiency is always going to be how much useful work you got out of something compared to how much energy you had to put into it. So 5.8 over 8.2 is 0.71. And assuming the engine can be modeled as a Carnot cycle, calculate the temperature of the hot reservoir. For Carnot engines, the efficiency is just 1 minus temperature low over temperature high, because this is the max or the ideal. There's always a linear relationship between QH and TH, and QL and TL. So 0.71 is equal to 1 minus 373 over TH. Multiply both sides by TH, you end up with a high temperature of 1,274 Kelvin. We have our Carnot cycle again. Remember, for Carnot cycle, isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression. All right, all reversible processes. Identify the part of the cycle which the energy is transferred to the gas. So remember, there's no heat in the adiabats. So BC and AB are out. So we are dumping energy in on AB, and we're pulling the energy out on BC. All right. Oh, sorry, CD. I said that wrong. So ABQ is positive, dumping heat into the system. CDQ is negative, pulling heat out of the system. The efficiency cycle is 0.4. The work done during one cycle is 960. Calculate the energy transferred into the gas. So efficiency is 1 minus QL over QH, or you could also say it's just the work, net work over QH. Just a couple ways of deriving that. Since we know the efficiency is 0.4 and we know the work done is 960, we can just use this form of the equation right here. And QH is going to be 2,400 joules. That's how much is transferred during one cycle. And then how much is removed, we can just go to the other form of the equation right here, now that we have QH, and solve for QL. We got 1,440 joules come out of the cycle. Or you could just say, hey, what plus 960 is going to be 2,400. For 12, we got our heat engine. 0.3 can be modeled as a Carnot cycle. Engine rejects waste thermal energy into a cold reservoir of temperature 150 degrees Celsius. Engineer wants to improve the efficiency of the engine to 0.5 without changing the temperature of the hot reservoir. Suggest how this can be achieved. Well, you got to find the temperature of the hot reservoir because you can't change that. So I solved with the 0.3 efficiency. And if we're at 150 degrees Celsius, please don't forget all of these are dependent upon using Kelvin, an absolute temperature scale. So our hot reservoir is at 604. If we want to change this so that it's now 50% efficient using the exact same hot reservoir, that means clearly we got to drop the temperature of our cold reservoir. And so when you find that out, you got to go from, looks like, 450 to 302. You got to drop your cold temperature by about 30 degrees. Oh, no, 150 degrees. Sorry, I can't subtract. 120 degrees. All right, 13, we have heat engine. They give us a diagram up there. Sorry, I didn't draw the diagram on here. And working substance is a monatomic ideal gas. Works on a reversible cycle in the PV diagram. Change AB is isothermal compression. So we have an isothermal, so TA is equal to TB. Change in BC is isovolumetric heating, and CA is an adiabatic expansion. The volume of the gas at B is 1/3 of the volume at A. So at A, the pressures, they give us some numbers here, 9 times 10 to the fourth pascals. The volume is 1.2 times 10 to the negative third meters cubed, and the temperature is 400 Kelvin. So because they're asking AB is isothermal, we can do PV over T is equal to PV over T, and the T's will cancel out. So that allows us to find our pressure at B, very straightforward. And then it says the temperature at C. So the problem is the temperature at C, C is an adiabatic process from C to A. So we know the pressure at A, the volume at A, and we're trying to find the pressure at C. Do I need the pressure at C? Oh, this is the way I did it. I found the pressure at C first. And then once I had the pressure at C, I could then go back to this formula here to find the temperature at C. But I had to use the adiabatic formula to find my pressure at C, because it was an adiabatic relationship between A and C. So that's how I did this problem using the 5/3. And once I had that pressure, I could then plug into PAVA over TA is equal to PCVC over TC. Remember that adiabatic, you have to think about that right there. The PVA to the 5/3 is equal to a constant. So then when I did that, I've got 833 Kelvin is my temperature at C. And finally, the thermal energy added to the gas during the change from B to C. Well, for this one, work is 0 because it's isovolumetric. So we can just say our change in internal energy is equal to Q. And since we know our change in internal energy is 3/2 NKT, and NKT is the same as PV, we can just throw it in like this and say that NKT is PV. So when you do that, the volume is the same because it's isovolumetric. So I just pulled everything out and had the pressure at C minus the pressure at B. When I worked that out, I got 175.2 joules. So that was A. And then B, it says determine the net work done. Oh, the work done in compressing the gas is 119. So find the net work done. Again, I made this little chart right here because I was dealing with a cycle. And so when I worked all this out, I found that my change in internal energy was negative 175.2. So that must mean on CA, because CA was my adiabatic. So my Q was 0 there. That my work done there was 175.2. And I knew my work done before was 119 during the compression, or negative, because the work being done on it. So I just took 175.2 and subtracted off 119, got 56.2 joules of net work done. And once I had that, the efficiency of the engine is straightforward, because you have 175.2 is your amount of heat being added to the system, and 56.2 is your net work. So you got 0.32 efficiency. All right, finally, 14. This one was long, just like the last one. I did a better job of diagramming this one for you. So we got pressure, volume, and we have monatomic gas, temperature of 320. So here's my 320 degree isotherm. Sorry, 320 Kelvin isotherm. Pressure is 1 times 10 to the 5th. That's nice. Volume starts off at 8 times 10 to the negative 4th. The gas undergoes a cycle that consists of 3 changes in adiabatic compression. So they gave me that volume. So it goes from A to B. Adiabatic compression would go up in temperature. Isothermal expansion from B to C. And then cooling at a constant volume to the initial pressure, C to A. So calculate at the end of the adiabatic compression, the pressure. So it's adiabatic, so PV to the 5/3 is PV to the 5/3. We know pressure and volume initial, and we know volume final. So we can solve that out. Got 5.1 times 10 to the 5th pascals. For the temperature, since I now know the pressures, I can now use this equation here to find my temperatures, because I know my pressure and volume at both A and B. So solving that out, I got a temperature at B of 616 Kelvin. Calculate the pressure of the gas at the end of the isothermal expansion. So in this case, the temperatures are the same. Temperature at B and temperature at C are the same because it's isothermal at 616. So we know pressure and volume at B, and we know the volume at C, so we just got to find the pressure at C. So the pressure at C is 1.9 times 10 to the 5th pascals. The graph, it says sketch the cycle on the graph, so I already did that right here. And finally, it got to complete our chart. The energy supplied to the gas during the isothermal expansion is 130. So the isothermal expansion is right here, BC. Got to have a change in internal energy of 0 because the temperature is not going up. So if the energy dumped in is 150, then the amount of work being done is got to be 150 as well, because it's work done by the gas. And it says the energy removed from the gas during the isometric cooling is 110. So the isometric cooling is this one, C to A. Isovolumetric. So that's got to be 0. So if we pulled out 110 joules, then our change in internal energy has got to be negative 110. So looking at the whole cycle, I can now fill in the change in internal energy from A to B is got to be it's got to be 110, which means the work done on the gas from A to B has got to be negative 110. So since we have 150 being done by the gas from B to C and 110 being done on the gas from A to B, our net work is 40. And if we have 40 going in, and this one, we don't have to worry about that negative there. We're only worried about how much heat got dumped into the system. And it was only dumped in at one cycle, B to C. So we got 40 out after putting in 150. So we got an efficiency of 0.27. All right. I know that was long, but I will see you all soon.